Hello, how are we doing, guys? We are on Thursday. It's whoops, and it's chemistry time. So who's been in maths and biology this morning? What are we doing today? Well, we are doing moles. Yeah, we're doing some mole calcs and stuff like that. I'm going to give you some techniques and some insights as to how to best attack these mole calculations and stuff like that. How are we doing, guys? So who have we got in here? Got Ruhab, Salma, Aisha, Dennis, Benyon, Faye. How are we doing? Good to have you back as usual, which is great. So yeah, we're going to do some more stuff. Louis as well, Shalane, Megan, Hillary, Ozzy, fantastic. How are we doing? The more the merrier here. Good to be back. Yeah. It's like Groundhog Day, isn't it, at the moment? But well, I suppose that's what it's like in college as well. You know, same lessons every day and stuff like that. Yeah, so we're going to be doing some mole calcs today. We are thinking about, well, how to best attack them, really. Okay, I mean, you know, I'm going to give you some truths. I'm going to give you some insights as to how I attack mole calculations and like the techniques I use and the ones I teach within the course and stuff like that. So who's the new people? Who we got some new people in here today, I think. Where's our newbies at? Welcome. You have caught us towards the end of the week, or end of the second week, in fact, you know, of all these lives that we've been doing. Hopefully you've caught up on the ones that we have been doing. And hopefully they've helped. You know, we try to cover as much as possible for you guys, try to give you a bit of structure. Now, of course, you're not doing going to school or college anymore. And hopefully that's working out for you guys. Now, the Exambulance course as well, that gives you some structure. We're just reworking that structure slightly. So the beginning of next week, it's going to be different. We're not going to be doing lives on YouTube anymore, but doing lives from directly within the Exambulance course. So it'll be dead easy. We'll show you how to do it. Essentially, it's going to be exactly the same, apart from it's just not going to be broadcast live on YouTube. It's just for you guys that are in the Exambulance course and stuff like that. So, you know, there's going to be a few changes in the way we're doing things, and we just want to structure the rest of your term, if you like, just to make sure that A, you finish the content, and B, you get some exam practice in. Because, of course, you know, you guys have been robbed of your mock exams at the end of year one as well, which is really, really sucky. No one likes doing mocks. No one likes doing exams, but the benefit of those mocks is, well, numerous, really. Obviously, you know, you get to figure out where you're at. Your teacher gets to figure out where you're at. They get to develop your predicted grades for UCAS and stuff like that. Yes, we are, Ruhab. Yeah. So tomorrow we'll talk more about what's going on in terms of the TT method and how you guys can apply it, and we'll set you guys off, you know, giving you a bit of a structure, but basically leaving to your own devices to a bit more now as well, because of course, you know, you've got the whole of the summer. So so you still having mocks online? Wow. Okay, so fair dues to your teachers if they figured out a way of doing that online for you guys. That's great. Okay. Hey, yeah, Nick. It's a tricky question about finding percentage mass. Question 2D. I have no idea what paper that is. I don't know what exam board it is, but I've got some lined up for us anyway today. Okay. Yeah, and in fact, Hillary, you're right. The chances are that your teachers, the first thing you're going to do is assess you in September when you walk back through the doors. Okay. You heard teachers are going to be giving grades to students and AQA just to prove it. Yeah, well, that's year 13 stuff. In the next hour, we'll talk about that. There's been some extra news, hasn't there? Like, there's been little bits kind of filtering out into the media about what's going on with those grades and stuff. So I'm not going to talk year 13 now because this is about year 12s. Okay, this is about year 12s. So I'm going to open up my blank piece of paper. Where are we? So what have we got here? Yeah, okay, I got a blank piece of paper. So mole calcs, ladies and gentlemen, mole calcs. So let's have some home truths before we get stuck into some questions. All right. So what you should be seeing now is my iPad screen, nice and blank. A few tabs at the top, maybe. There you go. They've disappeared. So what do we need to know in terms of mole calcs? Well, what you need to know in terms of mole calcs is very little, to be honest with you. Okay. First of all, formulae. Okay, really important. You need to be able to write formulae for different compounds. Okay, so if you think that the formula for sodium sulfate is NaSO4, then you're barking up the wrong tree, aren't you? It's Na2SO4. You need to be able to write the formulae for different compounds. Within the content guide, I've got a couple of videos on how to do that, swap and drop method. You got to know the charges on your ions and so on and so forth. Yes, absolutely, Hadia, yeah. So you need to get your formulae right, because if you don't get your formulae right, you've got no chance of balancing an equation. And that's what comes up next, okay? You need a balanced equation for any mole calcs that you do, okay? So you need a balanced equation. So that feeds into that. So get your formulae right. That means you can balance your equations correctly if indeed you need to write an equation for that specific question. All right, so that's the basis. Now, with a balanced equation, what you then need to do is actually be able to work with stoichiometry. Okay, so balancing your equation then leads into the stoichiometry of the reaction. So for example, I don't know, H2SO4 plus potassium hydroxide, that gives potassium sulfate and water. Okay, you need to be able to balance this. Okay, so it's really, really important that you get your balancing right. And then the stoichiometry, of course, what we're looking at is something like, this is a 1:2 ratio. This one here is a 2:1 ratio, like so. That's a 1:1 ratio. So basically, once you've got this stoichiometry in place, what you've got to remember is that if you know the number of moles of one thing, if I know the number of moles of H2SO4 in this reaction, then you know the number of moles of everything else using that stoichiometry. So that's your in, if you like. That is your first step in a mole calculation, is to whatever it is, okay, whatever the question might be. The question might be, what mass of potassium sulfate are we going to make? Well, the first thing you need to do is figure out, right, which one of those other reactants or products am I able to get the number of moles for? Now, that could be a reactant, or it could be a product. But basically, if you can find the number of moles of one thing in an equation, you know the number of moles of everything else, okay? So what do we do after that? Well, after the stoichiometry, that's where your calculations come in. So you need to find the number of moles of something. How are you going to do that? Well, you've got two options. Number of moles equals mass over molar mass. I use W for mass and big M for molar mass. So that could be a molecular mass. It could be a relative atomic mass. It depends on whether it's a molecule or a compound, or an element. The other one, of course, is number of moles equals concentration times volume. These are the only two you're ever really going to need. Okay, so that is everything. Okay, even right the way through to the end of year 2 mole calculations, it's all about those two equations. That is all you need. Now, of course, which one do you use? Well, it depends on the information you've been given in the question. Okay. Yeah, volumes of gases. Yeah, I mean, I suppose there are gas ones as well, which I'm going to talk about separately, actually. But by and large, you're going to use the number of moles is moles of mass over molar mass, or number of moles equals concentration times volume. Okay, so those are the only two you're really ever going to need. You might also have number of moles equals 24.0. So that's number of moles equals, oh, come on, Rich, get your triangle sorted. So it's number of moles times volume. No, come on, Rich. Yeah, number of moles, volume, and 24 decimeters, okay? Because 1 mole of a gas, of any gas in standard conditions, occupies 24 decimeters cubed, okay? So you can use that, that's your molar gas volume, of course, okay? So Megan, yes, stoichiometry is basically just the molar ratios. It's just a posh term for the molar ratios between them, okay? Which examples need to know the volume one? It's handy for everybody. If you look in your data sheets, a lot of them have that molar gas volume in the data sheet. If it's not in the data sheet and they want you to use it, then they'll put it in the question, okay? How about the number of particles equation? Well, yes, that is another one, but again, very rare. So in terms of number of moles, it's not really an equation that you need to remember, okay? If you're trying to figure out how many moles of something you've got, and you can use Avogadro's constant to do that. So that's all it is, just using Avogadro's constant. But like I said, by and large, it's these two bad boys here that are going to get you through most of your questions. Okay, going to get you through most of your questions. Now, what about hints and tips in terms of how to attack these mole calculation questions? Well, let's start with, so hints and tips. If you want to write these down, number one, draw out the info from the question. Now, we've done this previously, okay? So I think we were doing it with some other calculations we were doing, like enthalpy calcs and stuff like that. You're going to get questions which are really kind of word heavy, and they go into detail about the practical and so on and so forth, telling you what the student, this mystery student, was doing in a question. My advice is to draw out that information. So, right, okay, I've got the volume of H2SO4. Oh, I've also got the concentration of H2SO4. I've also got other information maybe about potassium hydroxide in the equation above. So you basically draw out that information from the question, and it makes it really, really easy. Okay. Find a molecular formula for molar masses. Yeah, that's another one as well. I mean, that's again not an equation. It's just understanding what molar mass is and how it works. Because all molar masses are in grams per mole. Okay, so that's how we work out the molar mass and stuff. Okay, it's grams divided by moles. Okay, that's it, and that's mass divided by number of moles gives you the molar mass. Hence, grams per mole. That's all that is. Okay. When you should do the mean titer or use the volume of something else? Well, yeah, we're going to go through a couple of titration questions. Okay, so my first hint is draw out the info from the question. My second one is to do a plan. Okay. So give yourself a roadmap of how you're actually going to calculate the answer. Okay, so actually say to yourself, see your route through, because that's most of the time the most difficult thing to do. Is like, okay, so I know what I'm supposed to do, but I don't know where to start. I don't know how to work my way through, and it's easy to lose yourself within those calculations. So my advice, and if you got the exam guide, whenever there's a big mole calculation, you'll see me do it in blue on the left hand side of the question in the analysis videos. I'm like, right, this is what I'm going to do. I know I've got that bit of information, so I can find the number of moles of that. Then I'm going to use a bit of stoichiometry. Then I've got the number of moles of this, which means I can turn that into a mass because I also have the molar mass. So it's like, give yourself a plan, a route through, and then it allows you actually to present your answer more clearly as well by doing a very quick roadmap of yourself through, right, okay, what information leads to what information. So it's like stepping stones to get to the final answer. All right. So my advice would be to do that. The third bit, in fact, I'm not going to call that number 3 because I think this is like the jewel in the crown, if you like. It is always 3 steps to the answer. Okay. By and large. Okay. 3 steps to the answer in any mole calculation, So step 1, that is find the number of moles of something, anything. Okay, now that links directly back to what I was saying before. Okay, if you can find the number of moles of one thing in the equation for the reaction that's taking place, then you know the number of moles of anything else. Okay, so whatever it is, it doesn't matter what it is in there, whether it's a reactant or a product, you'll have the information to find the number of moles present of something. Okay. Secondly, stoichiometry. So you're going to use stoichiometry to find the number of moles of the thing that you want. So the subject of the question, like, okay, is it the mass of potassium sulfate that I'm making is what I want. So I'm going to use the stoichiometry to go from here to here, which is a 1-to-1 stoichiometric relationship or ratio. Okay, so stoichiometry, that bit. Now, once you have that number of moles of the subject of the question, the thing you need, you just have to convert to the answer. Now, there might be a couple of sub steps in this third one, but essentially, once you've got the number of moles of something, Jacket, I'll tell you now. So once you've got the number of moles of your subject, so let's say potassium sulfate, the question will be, find the mass of potassium sulfate. Well, you'll have another bit of information somewhere, okay, in order to find it. Okay, in other words, the molar mass. You've always got access to the molar mass if you know the formula, because just have to look it up in your periodic table, right? So convert to the answer. So in other words, number of moles could be find the mass. You could find the volume of something, maybe given the concentration of it. You can find the concentration if you're given the volume. You could actually find the molar mass if you have the mass and the number of moles. So In any question, they're going to ask you to find one of those things: the mass, the volume, the concentration, the number of moles. Okay. So whatever that is, you need to convert your answer. Now, literally any question, and I'll show you in the examples that we've got today, there's those three steps to completing any mole calculation you come across. All right. And it's really important you remember those steps. It keeps it nice and simple. It stops you from panicking in an exam situation where you've got a big 5 mark and you're like, oh my God, there's some information, I don't know where to start. But if you just think to yourself, right, take a step back, 3 steps, find the number of moles of something, anything, that's your in. Even if you have no idea where to start or what the question's banging on about, I've never seen this practical before in my life, doesn't matter. You can find the number of moles or something because you've got 2 bits of information in the question that will allow you to do it. Okay. Then, of course, stoichiometry, and then you find the number of moles of what you want. And then, of course, you need to convert. So the definition of stoichiometry is the relationship between reactants and products in terms of a ratio, the number of moles you have reacting with each other in terms of a ratio. Okay. So, for example, sulfuric acid and potassium hydroxide is a 1:2 ratio. So the stoichiometric relationship, stoichiometry, is the term that I always use for that. Limiting reactant in relation in terms of stoichiometry. Okay, so yeah, that's another little kind of area there where sometimes, just sometimes, they give you the means to work out the number of moles of both reactants, and you have to figure out which one of those is the limiting reagent. The limiting reagent, the one that's not in excess, is the one that's going to dictate how much product you make. Okay. I always say, like, it's like pairs of shoes. If you've got 50 left shoes and 55 right shoes, how many pairs can you make? All right. So you're limited by the limiting factor, which is the left shoes. You can only make 50 pairs because you've only got 50 left shoes. Right. So, you know, it's that simple. And that's all you need to do is work out that which one is the limiting reagent just by working out the number of moles of each of those things. But very rarely do they ask you to do that. In my experience in the exam, most of the time they will say in the question, blah, 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 H2SO4 was in excess. So if you know that one of the reagents is in excess, then the other one must be your limiting reagent. Okay. So most of the time they will say one thing's in excess. So you can rely on the number of the moles of the other one to actually, use in terms of your stoichiometry. But like I said, very rarely will they get you to have to find which one the limiting reagent is. Yeah. What about the questions where 25 and 250? Yeah, I've got one of those lined up. So it's about spotting. And when you've got a practical question, it's really important you have a zoomed out view. You understand what it is that student's trying to achieve, what it is that student has done in terms of a method. And I think, rather than just plowing in and getting the figures, the first job you need to do is actually figure out, right, what is going on here? And you need to think step by step, what's happened to the, the reagent that may be dissolved in 250 and they're using 25 centimeter cubed of it in the titration. So you just need to look out for that in the question, and it comes at the end when you're converting your answer. Okay. So those are my steps. So make sure you've got those written down. I want you to remember those steps as we're going through these. Okay. If we get time, Hillary, yeah, we can talk about percentage yield and atom economy. Okay. So let's take a look at a question. Which one are we going to do? No, not that one, because that's a year 2 one. Oh, no. Go away. What have I done here? Go away. Pull me an iPad. Just go away. Right, well, that's not worked, does it? Right, here we go. Okay, so this is a typical titration question, okay? So we've got hydrochloric acid is prepared by dissolving hydrogen chloride gas in water. It's difficult to dissolve a known amount of hydrogen chloride, so the exact concentration of solutions is uncertain. A solution of hydrochloric acid of concentration between 0.95 and 0.105 was prepared. So they've given us some boundaries here. Before a class attempted the practical using the solution, a technician standardized the hydrochloric acid with sodium carbonate. So in other words, what they mean by standardized is actually find the exact concentration. That's what they mean by standardized, because we know it's between 0.095 and 0.105. We're just technicians trying to find out exactly what that is by reacting it with sodium carbonate. Technician dissolved 1.3 grams. So let's start making a note here, okay? So we've got 1.30 grams of sodium carbonate in water and made it up to 100 centimeter cubed. So we've got 100 centimeter cubed AQ of that sodium carbonate. The equation for the reaction done for us. That's kind of nice. You can see the stoichiometry in there really clearly. So that's 1 to 2 to 2 to 1 to 1. Okay, so any of those stoichiometric relationships will hold. So now a 10 centimeter cube portion of the sodium carbonate was transferred to a conical flask. So this is what we were talking about just now. Raseb was just asking about, what about these types of questions? So we're using 10 centimeter cubed portions of that, okay? And that's in the titration. So however many moles we find of sodium carbonate in our titration, well, obviously we need to multiply that by 10, okay? So 3 drops of methyl orange indicator were added in the solution and titrated with hydrochloric acid. Indicator at this point, neither here nor there, unless they ask us for the color change. The results are shown below. Complete the table to determine the concentration in moles per decimeter cubed of the hydrochloric acid solution, giving your answer to an appropriate number of significant figures. Well, we've got 5 marks here. So first job we need to do, in fact, I'm going to do this in blue, like I said I would. We're going to have to find the mean titer, okay, using the information in the table. Then what's the next step, guys? Once I've got my mean titer, what do I need to do? So just think, we have got our HCl in the burette, like so, and we've got our sodium carbonate, 10 centimeter cubed of sodium carbonate in there. Find the moles of something. Yeah, so you got times by 10. What can we find the number of moles of? Boom, Raseb, absolutely, okay? We've got our mean titer. This is a bit backwards because we don't know the concentration of the HCl, and that is our mean titer, isn't it? Okay, so we need to find the number of moles of sodium carbonate. Good. So we need to find the number of moles of sodium carbonate in 10 centimeter cubed, okay, because that's what's in one titration. And then from there, what can we find out? The number of moles of HCl where? Yeah, we can use the ratio then. So that's our first bit, our first step, find the number of moles. 2, bit of stoichiometry to find the number of moles, not in 100 centimeter cubed, because that's not the HCl. So if we know the number of moles of sodium carbonate in 10 centimeter cubed, using stoichiometry, we can find the number of moles of HCl in, nope. Think about it. We've got 10 centimeter cubed of sodium carbonate. We know the number of moles of that in there. So we can use stoichiometry to find the number of moles of HCl that reacted with it. So in what volume? In the mean titer, okay? So we know the number of moles of HCl in the mean titer, okay? And then 3, we find the concentration of HCl using number of moles divided by the volume in the mean titer. Okay, so it's just about, like I said, having a really clear understanding of what the question is actually banging on about, what's going on in the practical, and maybe doing a little diagram like this helps. So I've got 10 centimeter cubed of sodium carbonate in a conical flask. I've got a burette full of HCl, okay, and we want to find the concentration of the HCl. So let's do it together. Let's do it together, okay? So mean titer here was 26.00. This one is 24.00. This one is 25.10. This one is 24.05. And this one is 24.05. So give me some numbers, guys. Which number titrations are we going to get? Which number titrations are concordant? Give me some numbers. Megan, 245. 245, 245. Good. 1, 2, 3. Okay. So first things first, mean titer. Okay. I mean, I suppose we don't have to do this first, to be honest with you. We can find out later, but I'm just going to go mean titer equals 24 plus 24.05 plus 24.05 over 3. That gives me 24.03 recurring centimeters cubed. That's our mean titer. Okay, so as far as I'm concerned, all titers should either have a 0 or a 5 at the end. I mean, mean titer we can actually, calculate to there. So that's that bit done. So we need to find the number of moles of Na2CO3 in 10 centimeter cubed. So what's the first thing we need to do there? How do we find the number of moles of sodium carbonate in 10 centimeter cubed? Oh, yeah, it's 24.10. My bad. I was doing it in my head whilst I was talking at the same time. So that's 24.10. So that means that's 24.05. Okay, done. Thank you. Concentration times volume? Nope. 1.3 divided by 10. Good. We're using the mass, Megan. Well spotted. So we have got a mass, okay, and a molar mass to find the number of moles of sodium carbonate. So number of moles of sodium carbonate in 100 centimeter cubed, okay, because that's what it was initially dissolved in, is mass over molar mass. So that is 1.3 divided by, what was it? 106. I'll take that. So 1.3 divided by 106 equals 0.0123 moles. Okay, 0.0123 moles. Okay, Na2CO3, are you sure it's 106? 23 times 2 plus 12 plus 32, 48. Yeah, it is. Okay. So therefore, number of moles of sodium carbonate in 10 centimeter cubed equals a tenth of that, which is 0.0123 divided by 10. And of course, that is 1.23 times 10 to the minus 3 moles. Okay, so that is your first step, if you like. Okay, finding this. That's the number of moles of sodium carbonate in 10 centimeter cubed, basically what's sat in the bottom of your conical flask. Now we need to find out how many moles of HCl reacted with it. Okay, so this is step 2, the stoichiometry part, the number of moles of HCl in, now our mean titer is 24.05 centimeter cubed. That's what the volume of HCl that reacted with it. So the number of moles of HCl in 24.05. Jacko, why do you do in a tenth? Because if you read the question, before a class, it's where is it? The technician dissolved 1.3 grams of sodium carbonate in water and made it up to 100 centimeter cubed. A 10 centimeter cube portion of that sodium carbonate was transferred to a conical flask. So you've only got a tenth of your entire stock of sodium carbonate in one titration. Okay. So number of moles of HCl in 24.05 equals 1.23 times 10 to the minus 3. What am I doing here? So we're doing stoichiometry. I know the number of moles of Na2CO3. Boom, Benyon, absolutely. Times by 2. Okay, so we're working a path through. Okay, we're working a path through. So that is 2.46 times 10 to the minus 3 moles. Good. Okay, so we just multiplied it by 2. And then the last thing the concentration of HCl. So obviously we've done our stoichiometry. We've ended up with a number of moles of what we want. Now, of course, we need to convert it. We're converting to find the concentration of the hydrochloric acid solution. So concentration equals number of moles divided by volume. So that is 2.46 times 10 to the minus 3 divided by what? What's our volume? What volume have we just been working with? Not 10. 10 was for the sodium carbonate. Remember, you got to keep your volumes and concentrations of different things separate. Good. It's 24.05 because that is the volume of the only volume of HCl we've got access to. Okay, so that'll be 24.05 over 1,000, which is of course standard. So that is times 2 and then divide by 24.05 divided by 1,000, and that is 0.102 moles per decimeter cubed. Okay. Yes, Mimi, absolutely I will. I promise I will. Okay. So, as I said, it is a 3-step process. You need to do a bit of donkey work beforehand here, making your, finding your mean titer and stuff. But, that it's par for the course. All right. So what's really important here, okay, is if I just go back to, hang on a sec, I need to bring back my, was it this? Go away. One sec, guys. I just want to go back to my blank page. No, that's not what I want. Blooming technology. There we go. Back on it. Oh, I've done it again. May as well do this. Right. Oh dear. Just when you think they got the hang of it, eh? Oh, I'm glad you think that was a lot easier. Now, what you want to do is try and get this in your mind. Let's just take the example that we've just taken, okay? So we've got, oh, come on. Why wouldn't it let me write on it? Oh, what is going on with technology today? It's a conspiracy, I tell you. It's a conspiracy. I'll tell you what, I'll just use this. Right, so let's take the question we've just looked at. We've got HCl reacting with sodium carbonate, okay? So our HCl is in the burette there, and we have got 10 centimeter cubed of Na2CO3. What information did we have at the, yeah, it's not a power cut. What information did we have about these at the beginning? Okay, well, we had an approximate concentration of HCl. The only information we have on HCl is the volume, and that was 24.05. That was our mean titer. That is literally the only information we had that we could use on HCl. But for sodium carbonate, we had a mass, okay, which was 1.3 grams. We had a volume, which was 100 centimeter cubed, right? So also we've got the molar mass of sodium carbonate, which is 106. We could work that out, okay? But of course, the secondary volume that we had was 10 centimeters cubed, and that is what's in there, okay? So the first most difficult, and it's just, taking a view as to what information you've got about these two different reagents that you've got. Now, whilst we were going through, some of you are saying, oh, I asked what volume of HCl do we need to use in our calculation to find the concentration? Some of you said 10, some of you said 100, but you can see how they've got nothing to do with HCl, okay? They are all facts about sodium carbonate. So it's really important you try and dissociate the information you've got about your two reagents. And that way you don't get confused as to what relates to what. Okay, did I have the volume for HCl, or was that the volume of sodium carbonate? So, you know, even if you've got a separate bit of paper with you in the exam and you just do a list of information you've got about each of the reagents, then it really helps just that clarity of vision to actually see a path through, okay? Because the way I saw it, okay, if I could find the number of moles of sodium carbonate in that 10 centimeter cubed, then using stoichiometry, I could find the number of moles in that volume of HCl, and then working the concentration out is easy because I had the volume and I had the number of moles. That was 2.46 times 10 to the minus 3. Okay, so like I said, you need that zoomed out view. You need to be able to see where's information about that reagent, what information have I got about that reagent, okay? Yes, molar mass is MR. I use the term molar mass because you could be talking about relative atomic mass or relative molecular mass. So it could be either. So generic term is molar mass. Yes. Okay. So let's do another one. Let's do another one. So not that one. Not that one. Let's do this one. Okay. This is an OCR one. This is in the specimen paper for OCR actually, and this is just one where you've got a lot of work to do. Okay, so student carries out an experiment to identify an unknown carbonate. Student weighs a sample of solid carbonate in a weighing bottle. The tips the carbonate into a beaker and weighs the empty weighing bottle. Student prepares 250 centimeter cube solution of the carbonate. So our carbonate, so our XCO3, okay, we've got a volume. So the volume is 250 centimeter cubed, but then it carries out a titration using 25 centimeter cubed of it. So we're using 25 centimeter cube portions, okay? This solution is measured using a pipette with 0.1 molar HCl in the burette. So we're reacting HCl with that. The only information we've got about the HCl is the concentration, and that is 0.1 mole per decimeter cubed. Okay, so I've made those two lists. Okay, been really, really clear as to what information I've got about each one. Sample of carbonate is dissolved in about 100 centimeter cubed of water in a beaker, transferred to a volumetric flask. The volume solution is made up to 250 with distilled water. We've all made a standard solution, right? I'm assuming we've all made a solution in our volumetric flask. Another student suggests two possible sources of error. A small amount solid may remain in the water in the weighing bottle. A small amount of solution remained in the beaker. State whether other students' statements are correct. How could the procedure be improved? Now, I'm going to label these A and B. Which of those are correct? Which of those are a source of error taking into account the steps that the first student made? Is it A? Is it B? Or is it A and B? Or is it neither of them? You tell me, okay? Which of those would cause an error? A would cause an error, okay? Dennis and Ruhab straight in there. Jacka, Megan. Miss C says B. Louis says both. I can tell you that if you said A, you're wrong. The reason you are wrong is because of this. The student tips the carbonate into the beaker. So the student weighs a sample in the weighing bottle. The student then tips the carbonate into the beaker and weighs the empty weighing bottle. So what that student has done, is take into account any that's left in the weighing bottle. So they've weighed by difference, okay? They've weighed by difference. So this is not a source of error for this student with the method that they've done, okay? Now, a small amount of solution remained in the beaker. See, it's all about the question, right? The information's in the question, because your gut instinct, and you'd be right, if some got a lot left in the weighing bottle and they didn't bother reweighing it after, then yeah, it would be a source of error. But because of the fact the student reweighed it, it's not, okay? They've taken into account. But a small amount of solution remaining in the beaker is a problem, because what should they have done, ladies and gentlemen? What should they have done? when you got the beaker with it dissolved in, they put it in the volumetric flask and then made it up to 250. What should they have done with that beaker? Boom, Benyon, they should have washed it. They should have rinsed it and added it to the solution, okay? So the answer here, okay, state whether the student's statements are correct. A, not correct. B, is correct. What they should have done is rinsed the beaker and added to the volumetric flask. Okay, what does that do? Well, it minimizes losses, all right, because you're going to get some hanging around in that beaker. So there's a little fly hanging around in it. And that didn't get added to your volumetric flask. So what, you've got a very accurate mass that you went out of your way to get a decent mass to dissolve in that water. And then if you just left some of it in the beaker, you think you've got more mass in there than you actually have. So if you weighed out 10 grams, yeah, and then you dissolved it and you didn't rinse that beaker out, maybe a gram of that, whatever you dissolved in there, still in the beaker. So you think you've got 10 grams in the volumetric flask. No, you've only got 9. So that's, it's really important that you rinse those out. Okay. So on to some questions. The student carries out a final part experiment by adding the 0.1 molar hydrochloric acid to a burette, performing a titration using a 25 centimeter cube sample of the aqueous carbonate. So again, what I see in my mind is this. I've got HCl, that is 0.1 molar. In here, I've got 25 centimeter cubed of the random carbonate that we don't know what it is. Diagrams show the initial and final burette readings. Record the student's readings and the titer. So, of course, I'm not going to beat around the bush here. That starts at 0.6. That goes to 22.8. So our mean titer is 22.20 centimeters cubed. Okay, so that's our mean titer there. All right, just 1 mark. We can all do that. Describe what they shouldn't do next to obtain reliable results for a titration. The word there, really important. 1 word, please, ladies and gentlemen. What should the student do next to obtain reliable results for the titration? Boom. Good. Absolutely. Okay. So repeat what I would do. It would be tempting just to say, oh, repeat it. Repeat it. Like, this is an A-level exam. Are you going to get that 1 mark for just going, repeat it? For me, in there, you should have repeat it until 3 concordant titers are obtained. So you're getting that word concordant in there, and then you take a mean. So that's it. So repeat, get concordant results, take a mean. I would write those 3 things in there. This is about exam technique, don't forget, guys, okay? It's about, even if you go above and beyond what the mark actually wants in the mark scheme, it doesn't matter. Better that than just writing repeat and going and losing a mark for not saying get concordant titers and take a mean. Okay, concordant. If they are concordant, that means they are plus or minus 0.1 of each other. So they need to be within 0.1 of each other. Okay, that's it. Exactly. Right, calculation time. The equation below represents the reaction between the carbonate and hydrochloric acid. So you got M2CO3. Now, for a kickoff, ladies and gentlemen, tell me what group that metal is in. We got this unknown carbonate. What group's it in? Miss C says 2. Resurrection Stone says 1. Oh, we got 2, 1, 2, 2, 2, 1. The answer, ladies and gentlemen, is 1. The reason we know this is because CO3 is a 2- ion. If we've got 2 of those metals in there, that must mean they must have a 1+ charge each, and therefore it must be a group 1 carbonate. It must be a group 1 carbonate. The other reason, okay, why it can't be a group 2 carbonate solution is what? Why can't it be a group 2 carbonate solution? Waiting for that answer. Good, Hadia. Yeah, absolutely. And loads of you are on this, okay? They are insoluble. And it's just another little chemistry fact that really helps you along the way, okay? So they're not soluble at all. Okay, calculation time. Calculate the amount in moles of M2CO3 used in the titration. So the titration, what information do we have? So We've got, hang on, calculate the amount in moles of M2CO3 used in the titration. Oh, okay. So we've got our mean titer and we've got our concentration of HCl, okay? So first thing, number of moles of HCl in mean titer equals concentration times volume. So that is 0.1 times 22.2 over 1,000. So what's that? That is 2.22 times 10 to the minus 3 moles of HCl in our mean titer. Second up, stoichiometry. So therefore, what do we need to do with that number to find the number of moles? Good. Number of moles of M2CO3 in 25 centimeter cubes. Why do I know it's in 25 centimeter cube? Because that's the volume of M2CO3 that's in the conical flask for this titration. Okay, so we divide that by 2. So it's 2.22 times 10 to the minus 3 divided by 2, and that equals 1.11 times 10 to the minus 3. And that's the number of moles. So this is just the first 2 steps, if you like, of the 3-step process, okay? So the student's mass readings are recorded below. Use the student's result to identify the carbonate. So this is where we employ a different mole calculation, okay? So this is, up here, we used number of moles equals concentration times volume. Down here, we're using number of moles, is mass over molar mass, okay? Thank you very much. Are we all agreed 1.58 grams? So the mass of the carbonate equals 1.58 grams. I'll take your word for that, okay? So therefore, the number of moles, the number of moles of M2CO3 in 25 centimeter cubes equals 1.11 times 10 to the minus 3. Now, yes or no answer, please, ladies and gentlemen. To find the molar mass, do I do 1.58 divided by 1.11 times 10 to the minus 3? Yes or no? Not a trick question. Louis says yes. Okay, let's go with that. So the MR, or the M of M2CO3 equals mass over number of moles. So that is 1.58 divided by 1.11 times 10 to the minus 3. Equals 1,423.4 grams per mole. Those of you that said no, why is it no? Because it's a ridiculous answer. There should be alarm bells ringing in your head right now going, well, it can't be that. Nothing's that big, right? It can't be M2CO3 and have a molar mass of 1,423. Good. It's way too big. Why is it too big? Because this is the mass that got dissolved in 250 centimeters cubed. This is the number of moles in 25 centimeter cubes. Okay? You got to remember, go way back to the beginning of the question and just check, right? So that was the mass that got dissolved in 250. So what we need to do is, okay, this is actually what I would say here. In fact, if I select all of this and move it down, get rid of that. What I would actually do here is, therefore, number of moles of M2CO3 in 250 centimeter cubes equals 1.11 times 10 to the minus 2. I've multiplied it by 10, yeah? So now, if we do this, 1.11 times 10 to the minus 2, that is, now that's better, 142.34 grams per mole. Okay, that's our molar mass. But that's not the question, is it? The question isn't find the molar mass of M2CO3. The question is identify M2CO3. So last quick thing here, ladies and gentlemen. Good, Yaz, absolutely. Okay, so 142.34 minus the CO3 bit. We know what the CO3 bit is. It's 1 carbon and 3 oxygens. Okay, so that is minus 12 and minus 48 for the oxygens. So that leaves us with 82.34. So M equals 82.34 divided by 2. Good, because the formula is M2. It's divided between both of those. So that equals 41.17 grams per mole. So M equals rubidium. Is it rubidium? I don't know. 41. It's not rubidium. It can't be calcium. Remember, it's group 1. It's got to be group 1. Are we agreed on potassium? I think it is 40.1, isn't it? Potassium or something like that. No, it's not. It's not 40.1. Yeah, K. Okay, so N equals K. So it is K2CO3. Okay, and again, just that little bit of info about, oh, it's definitely a group 1 metal. That helps us with getting the answer of this. Okay, 39.1. So yeah, I mean, it's close enough, isn't it? It's never going to be exactly the relative atomic mass you see in the periodic table. It's just as near as damn it. If you're a million miles out, then something's gone wrong with your calculation. Okay, they're not just going to give you the marks, all 4 marks for saying K2CO3. You've got to show your workings and so on and so forth. Okay, but yeah, it's definitely the closest, so it's got to be K. All right, so hopefully that time has flown by today, guys. Absolutely flown by. So hopefully that's helped you in terms of some hints and tips as to how to go about these mole calculations. Okay, I'll have to give you the question on why it's not exactly. I mean, there are errors in the practical errors are a whole different ball game. Okay, so it could be that the errors lie in the titration. They could have overshot the endpoint. They could have undercooked the endpoint. Yeah, actually, if we've got an answer bigger than what we think it is, have a think about what does that mean for your titration? Did they overshoot it or did they undershoot it? Okay, undershoot it, undercook it, overshoot it, and undercook it. Yeah. Okay. Are we going to do A-level calculations? I mean, basically, like I said, I mean, this whole kind of exambulance setup is going to change a little bit. We've had a rethink in terms of what it is we should be doing in terms of our time and how best we can help you. So the answer is, well, yes and no, really. Of course, these principles, though, they absolutely apply to A-level calculations, okay? You're kind of left to your own devices in A-level papers a bit more. AS papers tend to break the questions down into more bite-sized chunks. In A-level papers, you can get like 6, 7, 8 markers, just like question at the top, full blank page, and they're just like, right, find the molar mass of M2CO3. No worries, my pleasure. Okay, so hopefully you've taken some stuff away. Remember that rule that I taught you before, okay, or the things that you've got to remember. Make sure your formulae are correct. Make sure you write a balanced equation that it's correct if they haven't given you one, and then from there you can use your stoichiometry. All right. Now, 3 steps to mole calc heaven, ladies and gentlemen. Find the number of moles of something, anything. Okay. Stoichiometry to find the number of moles of something else, and then convert it into whatever it is you need, which is the concentration, the mass, the volume, whatever. Okay. So in terms of if you want more titration calculations, what you can do is, in the exam guide, all the mole calculations for anything are all in one place. Don't be afraid of trying other specification ones as well, because mole calcs are mole calcs, all right? So in the exam guide, you can look up mole calculations and you'll see all the mole calculations there and titrations and everything, okay? So it's about clarity. It's about drawing the right information out, have that zoomed out view, understand what's going on, okay? So you've got a big stock of solution, but you've only used a tiny bit of it in your titration. So when you're working backwards, you need to like blow that up again. So if you got 10 moles in your titer, then you're going to have more in your stock solution, aren't you? And sometimes, like we've just seen, you need to find out how much is in your stock solution. So just be wary of those things, okay? Try and get a zoomed out view. Tell the story to yourself of what's going on. Try and put yourself in the shoes of the student, and then you'll be absolutely fine, okay? So it just takes practice, okay? So tomorrow, I think in the second year class tomorrow, we'll be talking about the TT method. So I'm going to do, in fact, I don't know, I might combine the two classes tomorrow. It'll be clear. In the morning, you'll see on YouTube exactly what's going on tomorrow. I promise you that. But I will be back tomorrow to talk some chemistry, to talk about the TT method, and to talk about what the Exambulance is going to do for you over the coming months. Okay. So yeah, back titrations are another thing. I've got those within the course as well. So yeah, I'll open up some stuff in there for you guys to have a poke around with. I promise I'll do that today, and just to cover the last few days for you. Okay, so I'll make those previewable. All right. So, it'll be even better. Oh, absolutely. Yeah. We're all over this for you guys. Okay. It's going to take some obviously self-study and some self-motivation and stuff, but we're here to guide you, and we're going to be on hand to help you every single day. Okay. So just watch out for that. I don't think so, Jacka. You follow those rules, A2? Yeah, walk in the park. Once you've got a hang of it, of calculations, and you've got a technique, and that's why I'm here to help you, then yeah, you'll be absolutely fine. Okay, so final salute for AS for today, and I will see you guys tomorrow.